Hey everyone, let's jump right into this explainer and unravel the incredibly cool physics behind the thermal properties of matter, the stuff that completely governs our everyday lives. Have you ever paused and wondered why the physical world around you behaves exactly the way it does when things get hot or cold? Well, today we're going to break down this chapter and absolutely master those everyday mysteries. We all have these built-in, common-sense notions of hot and cold, right? But asking a simple question, like why a completely stubborn metal jar lid suddenly loosens up after you run it under some hot water, opens the door to understanding how energy physically alters matter. I mean, it's something we've all done. You run it under the hot tap, give it a little twist, and pop! But what's actually happening down at the molecular level? To make sense of all this, we're going to break this chapter down into 6 distinct concepts. We'll hit heat versus temperature, the measurement of heat, expansion and specific heat, the 3 modes of heat transfer, radiation and black bodies, and finally, Newton's law of cooling.
All right, starting with part 1, heat versus temperature, defining the invisible.
Here's the thing. In physics, just saying something is hot or cold isn't precise enough. And the crucial takeaway here is that heat and temperature, they are actually not the same thing at all. Heat is the actual energy in transit. It's the physical energy being transferred between systems because of a temperature difference, and we measure that in joules. Temperature, on the flip side, is merely the relative gauge indicating the hotness or coldness of a body. Think about leaving a hot cup of tea on the table. Heat flows from the tea into the cooler room until their temperatures match. Basically, heat is the mover and temperature is just the measure. Moving right along to Section 2, the measurement of heat, scaling the hot and cold. So now that we know what temperature actually is, how do we establish a totally universal way to measure it? Scientists needed an absolute baseline. By looking at the ideal gas equation and observing how pressure and volume decrease as things get colder, they extrapolated backwards and deduced an absolute 0 point. This is the ultimate freezing point where every single substance in nature has the absolute least possible molecular activity. The molecular motion just essentially stops. And this incredible deduction gave us the absolute baseline for the Kelvin temperature scale. And that brings us to 273.15. This number is literally the magical bridge between the high-level science lab and your kitchen. See, the size of a single unit in the Kelvin scale and the Celsius scale is exactly the same, so finding the Kelvin temperature is as simple as taking your Celsius temperature and adding 273.15, meaning 0 degrees Celsius, the freezing point of water, is a rather chilly 273.15 Kelvin.
Okay, with our measurement scales firmly locked in, let's look at Section 3, expansion and specific heat, matter in motion.
Let's talk about how heat physically changes the dimensions of objects. Picture an old-school blacksmith fitting an iron ring onto a wooden cartwheel. It brilliantly illustrates thermal expansion in action. The iron ring starts out slightly smaller than the wheel itself, but by heating the iron, the metal literally expands. The blacksmith slips that expanded, glowing hot ring over the wood, and as it cools down, it contracts, forming a perfectly tight, permanent fit. And hey, this is the exact same principle that loosens that stubborn metal jar lid we talked about earlier. The hot water simply expands the metal lid a lot faster than the glass jar. But here's a kind of fascinating quirk about matter. Not all materials heat up equally. This all comes down to a concept called specific heat capacity. It's exactly the amount of heat required to change the temperature of a unit mass of a substance by just 1 degree. It perfectly explains why, when you put a pot of water on the stove, the metal pot gets burning hot to the touch way before the water inside even begins to simmer. Water has a much higher specific heat capacity, meaning it takes a massive amount of energy to change its temperature compared to the metal pot.
Which leads us perfectly into Section 4, 3 modes of heat transfer, how thermal energy travels.
We all know heat flows from hot to cold, but how exactly does it get from point A to point B? Heat universally gets around using 3 distinct mechanisms. First up is conduction. This is heat transfer through solid contact, basically molecular collisions passing the energy along without the actual material itself flowing anywhere. Second is convection, which is the actual physical bulk motion of fluids like liquids or gases moving around. And third is radiation, where energy travels via electromagnetic waves, which requires absolutely no physical medium at all to get where it's going. Let's zoom in on convection for a second, because it's literally powering the world around us. Natural convection is entirely driven by gravity and buoyancy. When a fluid is heated from below, it expands, becomes less dense, and it rises up, while the cooler fluid sinks to replace it. This cycle powers everything from the circulation of blood in our bodies to the sea breeze you feel on a beach. During the day, land heats up faster than water, right? So the hot air over the land rises and cooler air from the ocean rushes in to take its place. But after the sun goes down, the land cools off way faster than the ocean, and that entire convection cycle completely reverses.
Next up, Section 5, Radiation and Black Bodies. Energy across the void.
So, conduction and convection both need physical matter to operate. But that raises a pretty massive question. How does the Earth receive heat from the sun across millions of miles of completely empty vacuum? The answer is thermal radiation, electromagnetic waves traveling at the speed of light. And the specific nature of this radiation is governed by Wien's displacement law. Simply put, this law mathematically proves that as a body gets hotter, the wavelength of its most intense emitted radiation actually decreases. It's the exact reason why a piece of iron sitting in a fire turns from a dull red to a reddish yellow, and finally to a brilliant, blinding white hot as it absorbs more and more thermal energy. When you chart out this radiation energy against its wavelength, Wien's law becomes super clear. Take a lamp filament burning at 2000 Kelvin. Its peak energy output is way over in the longer wavelengths. But if you look at an arc lamp at 3000 Kelvin, and then finally sunlight blazing at 6000 Kelvin, that peak sweeps dramatically to the left. It shifts right into the shorter, visible wavelengths of light as the temperature climbs. What is absolutely mind-blowing about these blackbody radiation curves is that they are totally universal. They don't depend on the specific material at all, just the temperature. Because of this, astronomers can accurately estimate the surface temperatures of celestial bodies just by looking at their light. By finding the peak wavelength of the moon's faint glow, they can confidently calculate a surface temperature of 200 Kelvin. And for the sun, that peak precisely corresponds to a surface temperature of 60 Kelvin. Finally, let's hit our last section, Part 6, Newton's Law of Cooling, the cooling coffee conundrum. Bringing it back down to Earth from the roaring surface of the sun, how do things actually lose all this heat we've been talking about? Well, Newton figured out this incredibly simple but profound rule for heat loss. The rate of cooling of a body is proportional to the excess temperature of the body over its surroundings. Basically, this just means the hotter your cup of tea is compared to the room it's in, the faster it's going to lose its heat to the environment. And as its temperature drops closer and closer to room temperature, that rate of cooling slows way down. So, to wrap up this explainer on the chapter, the next time you're waiting for your morning coffee or tea to cool down, ask yourself, how are the universal laws of radiation, conduction, and convection literally swirling around inside your cup? Because honestly, the coolest takeaway here is that the exact same thermal properties dictating the fate of your hot drink are the very same laws determining the burning temperatures of the stars in the night sky. Keep exploring the science hidden in plain sight, and I'll catch you in the next explainer.